In this video, I want to focus in on Chapter 5, Lesson 2. This chapter is about geometric proofs. Same as the last video, I want to start off talking to you guys about some vocabulary. Again, geometry is a very vocabulary-heavy chapter, and I want to make sure we are clear about the different things we're looking at. So we're going to use the flowchart to review the proof process. This whole thing is going to be talking about how do we write proofs? What is a proof? Heck, how do we go about proving something? Let's start with these three pieces. In order to write a proof, this first bubble says use inductive or deductive reasoning to write a proof. But what is inductive and deductive reasoning? Let's fill those in below. Inductive reasoning, first one, is the process of making conjecture. Conjecture is a specific word which just means we're making a conclusion. So this is more of the process of making a conclusion after observing examples. So inductive reasoning could be as simple as you could see that every fifth person that walks through the front door happens to be female. So you draw the conjecture or conclusion that the ratio to male to female students is 4-to-1. Well, that may not be true. That might not be fact, but for what you observed, it is true. Now, a proof. A proof is a logical argument where each statement, so every statement that we make, is justified or is followed up with a reason. So far, two definitions. They're kind of lengthy, so make sure you pause anytime you need to in order to get down this information. Deductive reasoning is a bit stronger, and deductive reasoning uses facts, rules, definitions, or laws to make conjecture or draw conclusions. And deductive reasoning is where we are going to focus on for this lesson, because we're going to use some of the rules and definitions we learned previously, as well as just our simple rules for solving an equation to create some proofs using some geometrical figures. Now, before we go into the proofs, there are actually two types of proofs we're going to see. For the purpose of this video, we're going to focus in on two-column proofs, but we're also going to talk about the paragraph proofs right here on this page. As the title might make clear, a paragraph proof is where we write a paragraph to explain. So we're going to use a paragraph to explain why a conjecture or conclusion is true. You guys have actually done stuff similar to paragraph proofs as you were writing essays in your ELA classes. It's the same type of structure. You would make a statement with some sort of explanation in order to reach some sort of logical conclusion. A two-column proof, again, where we're going to focus more on, is a proof that contains statements and reasons, like any proof should, but it is organized in two columns. And you will see when I flip to the next page what that looks like. Before we go any further, I want to focus in on this one piece, the statements and reasons. We're going to have a reason for every statement we make in a proof. To do that, we're going to use what we call theorems. A theorem is a proven statement or conjecture, so any proven statement or proven conclusion. And a part to add to this is it can be used to justify statements in other proofs. So once we have something that's proven, we can use that in order to make further statements in other proofs, and it keeps it logical and formal. So with these definitions we have here, again, pause, go back, and make sure you have each of these pieces. I'm going to move on to the next page, and on that page, we're going to see what a two-column proof looks like. And we're going to talk about what task you guys are going to be expected to do. So before we get started, your book lays out the proof process. It's always very important to have a process for putting together these proofs or putting together any argument. So let's see what we have. Step 1, list the given information or what you know. If possible, draw a diagram to illustrate this information. For our purposes, you're going to have the given information and a picture available. All you got to do is plug it in. We want to state what is to be proven. So every proof statement, so every problem you'll see will have some sort of proof that something equals something else. It could be like x equals 5. And we're going to use whatever we can to actually find that x equals 5. That hypothesis, the part we're proving, is actually going to end up being our last statement in any proof. Step 3 would be to create a deductive argument by forming a logical chain of statements linking the given information to what you're trying to prove. So deductive. For deductive, remembering we're going to have to use our facts, rules, definitions, and laws to make these proofs. And of course, in step 4, we're going to have to provide what's the name of that fact or that theorem or that rule or definition. And then again, we follow up by stating what that proven statement is that we talked about in number 2. Now, it's still very abstract until you have seen what an actual 2-column proof looks like, and that's what this video is going to focus on. All right, so here is what a 2-column proof looks like. I cut this one out of your textbook. Let's take a look at what is happening in this example. So, we want to complete the proof in front of us. We have our statement we're trying to prove here at the bottom, and all of our given stuff is right here. That given information comes from the actual picture in front of us. All of your given information can be found, or you should write on the picture that's given to you. Every proof is going to start with a very simple reason. The very first statement always has the reason that it is given. All you're going to have to write is given. That is our given information. It's already there. I didn't even have to do any thinking to get it. Now let's talk about the first reason we're going to have to come up with on our own. What I see here is we have this statement that the measure of angle y equals the measure of angle z. Well, we know that the measure of angle y is 2x minus 90. And the measure of angle z is x plus 10. It appears that for the next statement, they took the measure of angle y and plugged it in. Then they took the measure of angle z and plugged it in. The step they followed is a step that we simply call substitution. We're substituting known information to allow us to find an answer. Now, looking at the next statement, statement C, we went from 2x minus 90 equals x plus 10 down to x minus 90 equals 10. What happened here is they are using our rules for solving an equation to answer this question. They subtracted this 1x from each side of the equation so that all the x's were on one side. 2 minus 1 is just 1x minus 90 equals 10. So we call that the subtraction property of equality, which simply states that if we take and subtract the same number from both sides of an equation, which we did here and here, our statement, whatever we end up with at the end, is still a true statement. The left still equals the right. For statement D, it looks like they got x all by itself. So if we look at x minus 90 equals 10, if I wanted to get x by itself, instead of minus 90, I could say plus 90. I'm left with x equals, well, 10 plus 90 is 100. So all we had to do was add. And that's what we're going to name this reason. It is the addition property of equality. So using information we already know how to do takes us all the way back to when we first were solving equations. All we did was apply it to a little bit of geometry and used a logical process to find our answer. This is the format of the two-column proof. Now, not every two-column proof has subtraction, addition, or even division and multiplication. Also, there could be proofs where you're going to have to know and use the definitions from lesson 5.1 in order to make some logical conclusions. Let's keep moving forward and seeing if we pop into any of those. All right. This proof says, refer to the picture above. Ours is below for right here. Complete the two-column proof to show that if segment, the measure of EG, so line EG, this little piece right here, is 3x minus 1, and the measure of line segment ED is 2x plus 4. All right. And that EG is equal to ED. In geometry, we use a little hash mark to represent that those two pieces are equal. Then, so this part is our conclusion statement we see down here, x equals 5. Well, let's see what we find. That part that said if went as our first statement, our given. And they use a very important piece of information. EG equals ED. Well, I know EG is 3x minus 1, and ED is 2x plus 4. So they went and set those two pieces of information equal to each other in a step we call substitution. So very similar to our previous example, only instead of angles, we're doing it with segments of lines. Take a look at what they may have done to get from statement B to statement C. That 2x on the right seems to have disappeared. Well, if we were using, which we are, our steps for solving an equation, I see a positive 2x. Therefore, I would want to subtract 2x from the right side and the left to get rid of it, and 3 minus 2 is just that 1x we see on the left. So that's, again, our subtraction property. of equality. I know that's a lot to write. Your teacher, whether it's me or anyone else, may give you a way of shortening that just so we all are clear and we understand each other. From statement C to statement D, to get x by itself, instead of having x minus 1, they added 1 to each side. So again, our addition property of equality. I highly recommend you go back and you watch both of these proofs again. Go through it. Follow along. As you are listening, you should write this down. The more skills you put into it, listening, watching, and writing, the easier it is to actually retain the information. All right, so let's look at our reteach page. I want to go ahead and scroll all the way down to the bottom to this proof. This proof, if you look at it on the statements column, there is no equation that we're using. So we're not going to use some of the same tools we use in the last two proofs. Let's take a look at what we have and see what we can use. Use the figure to complete the reasons in the two-column proof to show that if lines B and C are parallel and cut by transversal A, then angle 1 is congruent to angle 3. That's really important. Look at that part I underlined in purple, the hypothesis. When we talk about parallel lines cut by a transversal, that's lesson 5.1. It'd be helpful if we pulled out the vocabulary page from lesson 5.1 to use as a reference here. Let's go ahead and fill in what we know. The very first line of this proof is again our given information. So let's see. I'm going to put these little triangles here. Just show that those two lines are parallel. Let's see what we have. They're telling us that the measure of angle 2 and the measure of angle 1 are congruent. Well, those two angles are on opposite sides of each other. If we recall, we call those vertical angles. So the measure of angle 1 equals the measure of angle 2 by the definition of vertical angles. Now we want to see if we can use this to find any other pieces of information. Is there something we can say about, say, these two angles right here? If we look at our notes from lesson 5.1, we have these two angles that seem like they're in the same position. Well, these are what we call corresponding angles, and we know that corresponding angles are the same or equal to each other. Now, there would normally be a lot more to that statement, but we're jumping some pieces just so we get the bare bones of what we're trying to solve. If we look, we have that the measure of angle 1 equals the measure of angle 2. The measure of angle 2 is equal to the measure of angle 3. And now the measure of angle 1 equals the measure of angle 3. So it seems like they took the measure of angle 3 and plugged it in for the measure of angle 2 and replaced it. Well, we know this is just called substitution. In fact, this is a special form of substitution, but we won't worry too much about that definition. I don't want to confuse you guys too much. Please go back, pause the video at any moment, and listen through these proofs again. There's a lot of different examples that we could use for proofs, an infinite number. So these examples might not be enough to get our understanding. So it's going to take a lot of effort and diligence on your guys' part.